for your response. Okay, let's see what number. Let's see. Close your eyes, everyone. Let's do number 65 because 65 is very similar to the one we just did. The other two here were bomb calorimetry problems, and I didn't want to do them right now just because I wanted to do something that we just went over. So we should be able to use the knowledge from the previous question to answer this one. So I'll give you some time to work on that one. Let's do, what do y'all think is a fair time? I'll give you more time just because, you know, yeah. So I'll give you 5 minutes, and if y'all finish early, just let me know and we can go and start. And if you finish, just let me know you finished in the chat. Style to fill and unfill. Oh, sorry, I'm messing up. This is my favorite section of Gen Chem 1. That might make me sound like a nerd. And honestly, I probably am a bit of a nerd, but I don't know. This is I don't know. It makes sense to me because this is stuff that you can apply every day. Like every time you dissolve salt and water for your spaghetti, chemical reactions involved in this are probably happening. Not that anyone cares except me. Yeah, that's what the next picture. Why is this up here? That's two days ago. It's more like a sidewalk in Austin, Texas. You have to draw them. Just show the diagrams. I would just copy and paste that over here. I think that's the exact same one. I'm gonna do that. Right? That's crazy. Yeah. I don't know. All right, maybe, what do we say? Where are y'all? Are y'all done? Put it in the chat. Yes, okay. So I'll go ahead and get started, so that way Sydney doesn't get bored and want to leave. So keep working on it, and then if you get it right, you can, check with the solution at the end, or if you just want to watch, you can just watch. So is this reaction, are we able to determine if this reaction is endo or exothermic? What do you see, Lauren?
It says no heat loss, so endo.
Yeah. So the heat lost to the calorimeter. Well, where does it say that? Assuming no heat, what this sentence means is that assuming that the cup, like this is a coffee cup, assuming the cup doesn't play a part in absorbing or releasing any heat. So let's just assume we have water in a reaction. Based on that, well, we see that the initial temperature of the water was 25 degrees Celsius. After the reaction, the temperature of the water is 23.34. So is the surrounding, we say our water is the surrounding environment. Is this water losing? It's decreasing in heat, right? It's decreasing in temperature, which means it's losing heat. If we say it's losing heat, the only place where that heat can go is to the reaction. So if the water is losing heat to the reaction, that means the reaction is gaining heat from the water. If the reaction is gaining heat, what do we say? Endo, right? So it's heat is going into the reaction, and it makes sense because we have a very strong ionic bond here between ammonium and our nitrate. And in order to break that ionic bond, it takes energy. So you have to put energy into that system in order to break those bonds. And that's what's happening here. So that's why the water decreases in temperature. Okay, so let me erase that. So we determined that reaction is endothermic. And from here, what we can also determine first is the moles. It's asking for the delta H, right? So what do we know the equation is for delta H of a reaction?
Reaction over moles.
Yeah, so delta H is equal to Q of reaction over the moles of whatever it was, all right? In this case, it's going to be moles of ammonium nitrate. And how do we know it's asking for delta H? Well, it's asking, saying, calculate the enthalpy change. H is enthalpy, change in enthalpy, right? Delta H. So the first thing we can probably do is the easiest thing, which is find the moles of ammonium nitrate that was dissolved, right? That's all that is just taking this number, 1.6 grams of NH4NO3, and dividing or multiplying by the molar mass, which for the molar mass of ammonium nitrate should be around 80 grams. I might be rounding, so 80 grams for 1 mole. And this should give you about 0.02 moles. Boom, look, we already got half of our equation. The next thing is to get the other half, which is Q of reaction. How should we go about that? The basic principle that you should be using for all these problems is the heat associated with one process is equivalent and opposite in direction for the heat associated with a different part of the system. So our reaction is one system, and our water is another system. Then we said this reaction is endothermic, so that means that the heat gained by the reaction is equal and opposite in direction or opposite in sign to the heat lost by the water, right? That's just the basic physical principle. And we know that heat of the water is equal to the MC delta T of the water, right? So plugging this variable into this very part right here, we should get our heat of the reaction is equal to our negative number, which we kept from this portion here, times the mass of the water, the specific heat of the water, and the change in temperature associated with the water. Right? From here, we plug in, chug all of our numbers. So we have negative number, negative sign still, times the mass of the water in grams, so 75 grams, times the specific heat of the water, which it says is 4.184, but again, that's not going to be given to y'all. So that should be something we memorize. 4.84 joules per gram times degrees Celsius. And then the delta T of the water. So it said the temperature, final temperature of the water, I'm doing this up here on the top left. Final temperature of the water is 23.34 degrees Celsius. And the initial temperature of the water was 25 degrees Celsius. This should give us a delta T of about negative 1.66 degrees Celsius. So we understand that, we know how to get delta T, and we just plug that part into here as well. And I know when negative signs start coming into the equation, it's a very scary thing because we want to make sure our thing is in the right sign, our final answer, right? But let's see. We have a negative here that we had earlier, and a negative that's associated with the temperature. Two negatives cancel out, which should give us a positive number, right? Well, we know that our reaction is gaining energy, so we denote that with a positive number. So our final number for a Q of reaction should be a positive number. And those two negatives canceling out give us that, so that's good. When we do that when we put that into our calculator, we get our Q of reaction is equal to 520.908 joules. All right, good. Now, what's the important thing about our units? What should our units be for enthalpy? Kilojoules, right? So now the next thing is just our basic conversion from joules to kilojoules. So 908 joules divided by 1,000 kilojoules in 1,000 joules in 1 kilojoule should give us 0.520908 kilojoules. So if we're able to get there, then we got both of the pieces of the puzzle that we need. I'll highlight them in orange. So our Q of reaction is this one. And then our moles was this one. So now all we have to do, we'll bring this back in purple. Last thing, calculate delta H. So delta H is equal to Q of reaction in kilojoules divided by the moles, which is equal to 0.520908 kilojoules over the amount of moles, which was 0.02 moles. Let me change my stuff here. So 0.02 moles. We found that in the green section, and then we found this number in the blue section. So it's all coming together to give us a nice, wonderful number of, let's see, 26 kilojoules per mole of ammonium nitrate, right? Is equal to our delta H. If you were able to do that one by yourself, then props to you. If not, there's a bunch of other questions like this on the review that once Rich sends that out, y'all should be able to start doing that over the spring break. And there's a lot of videos that we went over last semester on YouTube of going over these in class. So it's on our YouTube channel. You just have to find it. We didn't have like I guess when we posted the videos, we didn't put like, this goes over question, 41 through 45. You just kind of got to go through the videos. And yeah, but how do y'all feel about that question? 6 out of 10 in difficulty or in
No, like
confidence?
understanding, like confidence.
Okay, good. So that's good, because that means we feel more confident than we do difficulty, I guess. So again, with more practice, you'll realize, hey, it's not that bad. There's a similar process for each question. Every question is worded differently, so it might throw you off a little bit, but once you get the understanding of how to approach the question, then we'll be all good. Is there any questions on any part of this problem? Please ask now, because it's the best time to ask, right before you go into spring break, and then you're all alone to solve the problems. Anything that does not make sense? Okay, if not, then I guess y'all can, when do you plan on sending out the thing, Rich?
Probably this Monday or like today. Sometime between today and Monday.
Okay. All right, and there's one other person joined, so we want to make sure that they get the email as well. So before you go, let me just make sure we get everyone's name down. We got Lauren, we got Sydney's. Did you get James?
Yeah.
Okay. And then Ariana Diaz. So we'll make sure to send it out if y'all haven't got it already. Emailing Rich.
Thank you.
Have a good spring break, stay safe and be responsible. If y'all, let me stop recording.